Let me introduce to you an individual we'll call Patient X, a pseudonym we'll use for privacy purposes. A high school senior at the top of their class with a promising future ahead of them, they were diagnosed with acute myeloid leukemia. They underwent treatment for months. Fortunately, after 4 rounds of chemotherapy, they went into remission. They got to finish their senior year, getting to go to their prom and their graduation. Unfortunately, that following summer, they went into relapse. The cancer had come back, but it wasn't what killed them. After leaving the ICU where they were being treated, patient X contracted a bacterial infection from Pseudomonas aeruginosa, a multi-drug resistant bacteria found in hospitals. It can cause a variety of infections and can even lead to septic shock. Research has indicated that the mortality rate for patients with Pseudomonas aeruginosa infections is approximately 50% and accounts for around 10% of all hospital-acquired infections, or HAIs, according to the American Society for Microbiology. Pseudomonas aeruginosa also infects medical equipment, including implanted devices, another risk for disease transmission. In patient X's case, the infection was under their arm. And in the scenario that the infection spread to their bloodstream, doctors kept colistin as a last resort, a powerful antibiotic that can cause serious harm to the kidneys. As the infection got even worse, doctors gave patient X the antibiotic, but it didn't work. The infection first spread to their lungs and then their bloodstream, causing them to go into septic shock. It was fatal. Patient X passed away a year after their initial diagnosis with AML, but due to an antibiotic-resistant infection. Patient X's story is both heartbreaking and atrocious. Often, what is supposed to be a simple, brief visit to the hospital turns into a fight for survival. This is the story of millions of people from around the world who've suffered and died at the hands of a global epidemic, and what is quite frankly a threat against humanity: antibiotic resistance. Antibiotic resistance has become one of the most pressing challenges of our time. It occurs when microbes evolve to survive the effects of antibiotics. Resistance to antimicrobials, compounds that kill microorganisms, is actually an evolutionary trait designed by nature. But despite being a natural process, human factors such as poor sanitation practices, the overprescription and overuse of antibiotics, and inadequate infection control all accelerate the process. And we haven't done enough to limit our influence on resistance. Shortly after receiving the Nobel Prize in 1945 for his discovery of penicillin, Alexander Fleming, the father of antibiotics himself, warned us in an interview that misusing antibiotics can cause resistance. But clearly, we didn't listen. People of all ages are at risk for antibiotic-resistant infections. Hospitals are especially vulnerable, inhabited with both susceptible patients and a variety of pathogens. Not only are patients with already poor immune systems at risk, but so are the countless implanted medical devices whose surfaces can serve as a breeding ground for these pathogens. In fact, according to the Centers for Disease Control and Prevention, these HAIs are responsible for up to 1.7 million infections and close to 100,000 deaths annually in the United States. It's crucial that we find an effective treatment for this crisis before more lives are lost. But if powerful antibiotics aren't doing the trick, then what will? One way we can tackle antibiotic resistance is through bacteriophage therapy. A bacteriophage is a virus that infects bacteria. So how exactly do they work? Well, bacteriophages follow 2 different life cycles or methods of infection, known as the lytic and lysogenic cycle. The general steps of the 2 life cycles go as follows. They begin by attaching to the bacterial cell, where their genetic information in the form of DNA is injected into the cell. This phage DNA then replicates within the bacterial cell, where new phages are assembled. These new bacteriophages then express genes that damage the bacterial membrane and the cell wall, causing the cell to eventually burst or lyse. These new phages are then released to infect more bacterial cells. We've actually known about phages for over 100 years. They were discovered separately by Frederick Twort and Felix Durrell in 1915 and 1917, respectively. And they were actually used by the Soviet Union as an antibacterial. However, after the discovery of penicillin and the development of more antibiotics, bacteriophages were found to be difficult to produce, store, and prescribe in comparison. In addition, our understanding of viruses was quite limited at the time, so it made more sense to use antibiotics. However, the increasing urgency of today's antibiotic resistance crisis has rekindled an interest in these viruses. And we're starting to see the benefits of phages as compared to antibiotics. For example, phages are targeted or host-specific, meaning that they'll only kill a certain bacteria. This characteristic could be put to great use. As in humans, we can use phages that will only kill resistant infectious microbes and leave alone bacteria that are actually beneficial to us. This is highly advantageous compared to antibiotics, which can destroy our body's natural microorganisms, which keep us healthy. Aside from being targeted, bacteriophages are also ubiquitous. They're one of the most common biological entities on the planet and are found in a variety of natural environments, including soil, sewage, and water. And due to their rapid replication, significantly fewer dosages of phages would be needed as compared to the relatively numerous dosages often required of antibiotics. Upon learning about these viruses, I became quite intrigued by the idea of bacteriophages and wanted to see for myself the effect these viruses had on antibiotic-resistant bacteria. But I knew that in order to do this, I'd have to work in a research lab of some sort. So I sent an email to a few professors and explained my growing interest in bacteriophages. Soon, I got a placement at a lab that worked with them. When I started working in the lab, I did some preliminary experiments with phage and resistant strains of bacteria. I found that the bacteriophages weren't so effective against the bacteria, and this was because of the biofilms they formed. Biofilms are surface-associated communities of microorganisms embedded in a self-produced extracellular polymeric matrix, or EPS, a slimy layer that is fortified with DNA, lipids, and complex sugars, with dental plaque being a common example of a biofilm. This matrix prevents materials, including antibiotics, from passing through and infiltrating the bacterial cells protected inside, contributing to the overall resistance of the bacteria. In fact, biofilms can increase the resistance of a bacterium by 1,000-fold compared to its planktonic or non-biofilm counterpart. In my experiment, these strong, enduring biofilms had prevented the bacteriophages from entering the cell and killing it. I realized then that the problem of antibiotic resistance requires some form of a multi-pronged approach. What if there was something that could weaken the biofilm? Something that could be used in combination with the phage and allow it to get through into the cell and kill it. My mind went back to a few years prior. I did a science fair project on the effect of various plants used in traditional medicines on different types of food spoiling bacteria. I started to think, did these plants have a role to play in breaking these biofilms? The answer is yes. Since traditional medicine in many cultures around the world use a lot of plant-derived antimicrobials, they can synergize with phage therapy to tackle the biofilms, both chemically and biologically. Plants produce secondary metabolites, small organic molecules that are not essential for their growth, development, and reproduction. These include phenolics and essential oils. Secondary metabolites often deal with wound response and biological threats, including microbes. Many secondary metabolites have been shown to be antimicrobial against several drug-resistant bacteria. But more specifically, grapeseed phenolics have tremendous promise to be used in combination with bacteriophages, as they've been shown to have cell membrane disruption capabilities. But why is this important? Well, cell membranes and biofilms are somewhat similar. They're both barriers that envelop the cell and control the flow of substances into the cell. So with these similarities, there's a possibility that these grapeseed phenolics can have the same disruptive effect on biofilms as they do on cell membranes. More importantly, it could potentially weaken the biofilm and make it easier for bacteriophages to infect and lyse a cell, effectively eliminating the bacteria. Having all of the resources in front of me at the lab to do some hands-on research, I decided to investigate this concept further with antibiotic-resistant bacteria. I decided to use Pseudomonas aeruginosa, the multi-drug resistant bacteria I mentioned earlier. I started to incorporate grapeseed phenolics with bacteriophages, testing a variety of concentrations to determine the optimal mixture with the best effect on Pseudomonas biofilms, using new research techniques I'd learned earlier. Biofilms were first grown in microplates, where I would then add these various mixtures of phages and grapeseed phenolics. After, the microplate would then be placed into a plate reader, which would then measure the absorbance of the biofilms by determining the optical density of each well. The lower the optical density, the greater the effectiveness of the treatment. To make a long story short, the experiments ended up being successful. Multiple concentrations of the bacteriophage and grapeseed phenolic mixture showed high effectiveness against the resistant Pseudomonas. And this was wonderful news. But these experiments are just a small start requiring deeper investigation. And that's the nature of scientific inquiry. You start with an idea, you test it, and if it shows promise, you explore further. In my case, through more testing and modification, the combination of bacteriophages and grapeseed phenolics could be promising as a potential treatment for resistant Pseudomonas infections, including those in hospitals. And that's really exciting. But aside from thinking about the potential scientific applications of the research, it's important that we as researchers acknowledge the personal ones too. When I was working in the lab, I was very immersed in my experiments to the point where I often didn't consider the purpose of the work that I was doing. This suddenly changed one day when I was exhibiting my project at a public event promoting science fairs. At the end of the night, as I was packing up, a lady approached me asking me to explain my project. So I gave her a brief overview. She seemed quite knowledgeable on the topic, so I asked whether she worked in a related field. Her answer was completely unexpected. She said, actually, my sister died last month from a resistant infection. Throughout my experiment, I had read lots of numbers about deaths caused by superbugs. But when this lady told me her story, these victims became so much more than just a statistic. They became a human being. As we've been talking about hospital-acquired infections and resistant bacterial strains, I'd like to highlight that this is an ongoing problem. As we find the cure to one resistant bacterial species, another gains resistance, keeping us on our toes and searching for the next solution. And that's the nature of science and discovery. When a problem arises, we find a solution. And I think that seeking solutions to global issues has become so much easier and so much more accessible for everyone. In all of our pockets these days, there are new worlds of research just waiting to be easily discovered. Just do a search for something that interests you, something you think that could make a positive impact, whether that's on one person or the whole world, because you've no idea what it could lead to. Thank you.